Welcome to our presentation on anime character aging and de-aging. I am Ahmed Wael and my partner is Adam Hagazi, who will begin the presentation.
So this is the table of contents of the presentation we present today, starting with the problem statement. So our problem that we wanted to solve is that we wanted to create a model that ages and de-ages characters of anime from teen to senior and vice versa. So this is our expected input and output, such that we can feed the model with young characters and it ages them, and the senior characters and it de-ages them. Our original model that we based our model on was the implementing cycle GAN for age conversion by Matcha, which worked on unpaired data sets, meaning that we do not have to give it two pictures of the same character, aged and de-aged. And it also worked for human aging and de-aging, which was the closest to our problem. This is the architecture of the cycle GAN that we discussed in details in previous presentation. But as an overview, the GAN basically can map from domain X to domain Y. Here can be horses and zebras, while by mapping the main features of the domain Y, while still maintaining the main essence of the domain X. It also has two discriminators. One presented here of the discriminator Y, which compares the domain Y, the predicted Y, and the original Y. This is the output of the base model, which has original domain as a senior or a young character, human, and it ages them and vice versa as well. Then it reconstructs them back to their original domain. Moving on to our solution. So basically, our solution was to domain transfer the cycle GAN, as there was no current paperwork on that. So to overcome these challenges, we had to obtain our data sets of young character of anime characters and the senior ones. So we also had to scrape this data and do a lot of data cleaning on them. Now we also did data augmentation because of the data set size needed to be increased. We also did a lot of some model modifications and hyperparameter tuning as well, in order to make this model work well on anime characters, which had different appearance from human characters. So moving on to our progress report. As presented in the previous Milestone 1 presentation, we did scraping in order to obtain our data sets, and then we had to crop these images in order to be only for the faces of the anime characters. And also we discussed in detail our base model and variations. But in this milestone, we did data augmentation in order to increase the data set size, and also we embedded some quantitative evaluation that we'll discuss later. Starting with our data augmentation, we increased the data set of the seniors, which we had a lot of difficulty scraping data for, from 795 images to 2,385 images, meaning that its size increased by 3 times. And also we had to do this augmentation without distorting any faces. So we resorted to the flipping of the images horizontally in order not to distort the face of the character. And also we adjusted the brightness and contrast of the images. So that's how we did data augmentation.
Moving on to the second most important thing that we did this milestone, which is quantitative evaluation, which was part of our next steps in the previous presentation and part of the feedback by the professor and the TA. We used the Frecht inception distance, which is the most popular quantitative metric for evaluation of GANs. It was introduced in 2017, and it uses the Inception version 3 2015 pre-trained model. Essentially, it measures the similarity between two groups of images in terms of their feature vectors, and it is calculated as shown in the equation in front of you. Other small things that we did, but also very important that we did this milestone, is finalizing the pipeline for saving and loading the models, which was essential because we had a very large data set, which caused a lot of longer run times, and we needed to save and load the training progress at different time intervals. We saved the weights after every epoch, and we were also able to reload weights to generate data without continuing training. Both options were available. We also continued with our model variations, specifically in terms of batch size and input image size. And these are the values shown in front of you. And now let's discuss the results that we have and some plots and graphs. These are some of the output that we had when the image size was 256 by 256. And these are some of the outputs that we had when the image size was 128 pixels in each dimension. Let us look at the quantitative evaluation metrics that we considered, which we mentioned was the Frechet inception distance, or FID. As you can see, the first 5 entries in this table belong to the same run taken across different epochs, starting from epoch 4 up to epoch number 66. And we had a Frechet inception distance for the teen domain, which is A, and the domain B, which is the domain for seniors. And you can see we have another entry for the 256 by 256 epochs, and that was only one entry. We'll explain this when we show the graphs. As you can see, all those in blue belong to the same entry, and we can kind of tell that there has been an improvement in the beginning and then some sort of overfitting, which has made the FID increase. This is something that we might not have explained in detail, but FID is something that we want to minimize. So a large FID means that we are overfitting. The reason that we only have one entry for FID for image size 256 by 256 is that we had not yet streamlined the save and load pipeline of the model. So we're unable to continue training from the beginning because of the shortage in time. However, now that all pipelines are clear, then we should be good to go. Speaking of being good to go, our next steps are continuing hyperparameter tuning, this time in more detail in terms of image size, batch size, the optimizer that we use, and the model architecture. And we need to solve some hardware limitations, specifically in terms of the RAM, and that's something that we can do using the provided Google credit. Our contribution was a 50-50 split in terms of training and in terms of calculating FIDs for predicted images. And in terms of research and getting more code, Adham was more responsible for the data augmentation pipeline, and I was more responsible for the Frechet inception distance pipeline. However, we made sure to fill one another in on the technicality, and the code was shared between us. Thank you, arigato.